Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about matrix calculus. So let's understand. Let's set up the agenda first. So we'll discuss about vector derivatives first. Then we'll understand Jacobian, Hessian, and then matrix derivative. These are nothing but kinds of, this is first derivative, this is second derivative, but defined for certain kind of functions. Okay. Also, these are the names based on names of certain mathematicians. Okay, so that's why these names are there. Okay, so let's go one by one. Let's start with vector derivative. Okay, so what are vector derivatives? So we know vectors, right? So vector derivatives. And if you want, what is a derivative? So if you don't understand, if you don't remember your integration, differentiation, or calculus, so there are two parts, like linear algebra meets calculus. So there is a detailed video on derivatives which has all the calculus refresher. I'll put the link of that video in the description. Okay, so that is so we assume that you know what is a derivative. Okay, dy by dx, partial derivative dy by dx. So these things you know. Okay, so that's the prerequisite. Let's proceed. So if we have a vector, say for example, if you have a vector x is equal to x1, x2, like this till xn, n cross 1 vector. So how will you define its derivative? So this belongs to n dimensions r of n. So what will be its derivative? So this is a function x. Okay, so let there be a function. So this is that maps. Okay, so let there's a function which maps this vector, this n dimensional vector, to a scalar. So we cannot take a derivative of a scalar only. So these are just constants lines, right? So if there's a function which maps this vector, so if there's a function f which maps this vector from n dimensions to one dimension or a scalar, then we can derive. Okay, so this is a scalar, then we can define a derivative for this. So derivatives are for functions, right? So not directly, we cannot do a derivative directly on one, right? It doesn't make sense. These are numbers. So similarly on vectors, these are just the units of that. So there must be some function which maps a vector to some scalar value, and then we can take a derivative of it. And after that, we can define a derivative, okay, of this function df by dx. Okay, is also called gradient. So this is a function. This is also called df. This is also called gradient. So there is some function which maps your n-dimensional vector to a scalar, and then we are defining a derivative of that function. That how will the function change? What will be the gradient of that function? Because functions will have some, functions will be some curves, right? There will be some line like this or whatever. There's some curve. So at some point, what is my curve gradient? I want to know. Okay, in that vector space. So for that, I have this thing defined. For normal simple functions, x y is equal to x, you know, right? Dy by dx will be equal to 1, or x to the power n is nx minus 1, like this, you know, x to the power n. Log x is 1 by x, d by dx, the derivatives of these. But in case of vectors, how do we define? So the gradient will be defined as, so this will be a vector of partial derivatives. So this will be dou f, the same function derivative with respect to 1. This dou is your partial derivative, if you remember. This will be dou f by dou xn. So this dou is a partial derivative, means we are differentiating this function, whatever is the function, only with respect to x1, assuming rest other dimensions or rest other these variables are constant. Okay, that's what partial derivatives mean. That if you have multiple variables, say for example you have x and y, and something is changing both with respect to x and y, and if I want to take a derivative with respect to x, then I assume that the function is constant with respect to y. Only x is changing and y is constant. So a derivative of a constant is 0. So that's how we'll get. So we'll have a function which will be of both x and y, and finally we can do a partial derivative only and get the change only with respect to x. So that's what this gradient measures. That there are n dimensions, right? There are 1, 2, 3 n dimensions. So this measures the gradient or the change of that vector in first dimension, second dimension, and like this is measuring it in n dimensions. So derivative of this function which maps n dimensional vector to a scalar will also be a n dimensional vector. Okay, so this is also written as f dash, okay, f dash x also. Okay, and this will belong to n cross 1, same as vector. If your x is n dimensional, so n cross 1 we leave it and then it's just written as 1. That's redundant. Okay, so I hope that is clear. So let's understand this with an example. Say for example, what is your vector? Say for example, you have any vector x and you have any function x, that is A transpose x, okay, where A is a x is a vector and then A is another vector of constants. So your x is a vector x1 x2 like this till xn, and your A is a vector a1 a1 a2 like this till an, right? And I have defined a function which is mapping this vector x to a scalar, because you know that this A transpose x is like A dot x, and will get an output as a scalar value. What will be the value of A transpose x here? So you have a1, so A transpose will be equal to a1 a2 like this till an, and your x will be this only, this. So what will be your A transpose x? Fx is equal to A transpose x. This will be equal to a1 into x1 plus a2 into x2, this row into this column, and we take all the sum, and finally we'll get only one value, that will be a scalar. So this will be equal to a1 x1 plus a2 x2 plus so on till an xn. Simple vector multiplication, and this will be a one scalar value, because these all this, what is vector? Vector is nothing but a collection of scalars. These are numbers, product of numbers, and then you sum it up, finally you'll get one number. This is not some vector here. Okay, so this will be a scalar. Okay, so what will be your f dash x here? F dash x is equal to, we have to take, that will be equal to dou f by dou x1 dou f by dou x2, that is called dou, that this is d, this is dou, that is equal to doh, like that. So this is partial derivatives, dou, like this till dou f by dou xn. So let's do a partial derivative of this. Yeah, this will be equal to, what will be the partial derivative of this? This is your fx, right? And with respect to x1, so what will be the partial derivative of this? So here a1, only this term has x1, so only this term will be there, and rest everything will remain constant for this, because there is no x1 term involved. So we'll take a derivative of this function, this term only, and that will become x1 will become power 1 and remaining will be a1. So it will be a1, similarly a2, like this till an, and this is nothing but your a, which belongs to Rn. So your f dash x is of A transpose x is equal to A. Okay, this is how we do it. I hope this is clear. So this is a mapping, this function should map a vector to a scalar. So this is what it is mapping. This function A transpose is mapping it to a scalar, and that's what you have got. Okay, so let's see another one, a bit complicated and very frequently used. So this will be a bit lengthy derivation, but bear with me. Okay, it is worth understanding, and if you understand these two, then you can just play around and get the you can solve for other kind of vector derivatives also. So these two will set up the foundation for that. So for example, the other function fx is equal to x transpose ax. You will see such kind of vectors, this kind of combinations a lot. Okay, so what will be the dimensions? So your x here belongs to Rn. Okay, so this means this is your n cross 1, this is your 1 cross n ulta, and you need them to multiply. So your A should be n cross n, because the inner dimension should match. So your 1 cross n, I have to multiply this. This will be a matrix. This is a matrix. It's a square matrix. If you see n by n, so I have x transpose A and then again x. So this is finally, so this is mapping. So this is 1 cross n, n cross n, So 1 cross n, this will be 1 cross n here, and then finally n, this dimensions match. So finally you will have 1 cross 1 as a dimension. So the value what you will get out of it will be a scalar. So is this not this function mapping a vector to a scalar x, and f of x is mapping this vector to a scalar. Get comfortable with these notations. Okay, so we have this. So there is a function. Now how do we find the derivative of this? So what do we want to find? So we have to find f dash x or df by dx. So this is involving x transpose also, A also. And what will be the A matrix? Let's, okay, so your x, so let's define all of them. X is equal to x1, x2, like this till xn. X transpose will just be a row vector of this x1, x2, like this till an. This will be n cross 1, this is 1 cross n, that is 1 row, n columns. And then what will be your A vector? A is a n cross n vector. Sorry, matrix, this is not a matrix. So A is equal to, A will be equal to A11, A12, like this till A1n. This will be ANN, AN1, A21, like this. This is your n cross n. Similarly, there will be A transpose, that will be equal to, the rows will become columns. So this row, I'll put it as this column. So I don't know if this is clear for you. 1n, okay, this will be A2n, this will be A22, like this. Okay, so this transpose will be, this row will become a column here. So let's put it that way. A11, A12, and then this will be A1n, then A21, A22, all this will be transpose, this will be A2n. Similarly, this will be AN1 will come here and ANN will be here. I hope this is clear. This is also n cross n matrix. Okay, this is A and A transpose, this is your X. This is simple, this we know already. I have just written it down. Now you have to find out what is your Fx, that is equal to X transpose AX, that is equal to, now can we write it in form of summation? So we are moving from this, these are all terms, right? So we are moving on both the X and Y axis. So this is kind of summation because this is value sum. So let's write it down as a summation. This will be equal to sigma I equal to 1 to n, sigma j is equal to 1 to n, and what will be the value? Xi, okay, then Aij, because both I is equal to j anyway, and then xj. So I'm writing it in I and j format, but here I is equal to j. Okay, both are moving on the same dimensions, right? And A is a square matrix. That's why we'll get. So we have to find what is f dash x, that is equal to dy by dx, or the gradient. So this will be equal to nothing but, so for x we know, for fx, okay, f dash x will be, so just not f dash x, so just dy by dx. So if I just want to have this derivative, the vector derivative we know, right, what it is, dou y by dou x1, dou, if this is y, okay, any y, dou y by dou xn, yeah, this is f dash x, this is equal to y, okay, this is your y, and y is equal to fx, this is your y is equal to, and here we are doing f dash x. Let me be clear, f dash x, this is equal to dy by dx, and this is your dy by dx 1 to n. Okay, so there will be n such terms for this y, and y is your x transpose ax. So this is a summation of all this. So now focus here, there will be a lot of derivations here, so don't miss the step. So let's assume that there are n such, so let's take one representative and let's find, okay, and then we'll sum it up. So if I am able to find the derivative with respect to one of the elements here, this one, okay, any one element here, then I can sum it up over this. That's why I have written this as like this. I'll sum it up across all the n cross n dimensions to get the sum finally. n cross n. If I get one such entity, and then I can sum it up over all the n cross n dimensions, and I can get the final singular scalar value. Okay, so let's choose that. So for example, I have one dou y by dou x k. Okay, and let's the index. So we have to find out. Let's calculate dou y by dou x k, and then we will sum it up across I and j. Okay, we'll sum it up. So we'll just find one term, and then we'll sum it up across I and j, and then we'll get the value. So this is one unit, right? This is one value. This is your xk kind of thing. Okay, let's see. So here only your xk, I and j are varying both the directions. So I'll take just one of the entries, the kth entry, and then I'll sum it up. This is what I've written like this. And I'll take the derivative also of one element, and then I can sum it up. So I'll get the f dash x also in that way. Because, okay, so let's see. So now if you see one more thing here, okay, this I and this kth term will come once in both I and j, because I varies from 1 to n, so there will be a k, and j also varies from 1 to n, there will be a k. So there will be a k in both the sides. So let's break it down into two parts. So when I is equal to k, so when I is equal to k, what will this become? This summation, this summation can be written, this whole sum can be written as, so I is fixed at k, so this is the sum. Okay, so let me go to the next page so that you don't get confused. So this is what I'm talking about. This is your y is equal to, okay, and now I'm fixing I is equal to k. Okay, so what will this be like? So I have fixed at k, so only j will vary. So this I have taken one value. So what will be the final value? This implies this will be equal to sigma j equal to 1 to n. I have fixed at k, okay, and then ai will become akj and xj, like this. And when I equal to j, the same. So now I have fixed j is equal to k here, so it will figure on both the sides, right, on the length and the breadth, both the sides. So there also I'll get 1k. So this time this will be sigma I equal to 1 to n. xi will remain as it is. This will be aki, sorry, this will be aik, because I remains as it is, k, and xk. Okay, so this same term has been written in two ways, using, or not I equal to j, this is I equal to, this is j, both the sides I'm measuring, right? J is equal to k. Okay, apologies for the typo. So one side on ith dimension also I'll get once k, and on j dimension also once we'll get k. And I've just substituted the subscripts. Here I have substituted as k, and in the second time I have substituted j as k, and I has remained as it is. Okay, so I have broken down into two terms, one from I side, one from the j side. Then why can I write it like that? Y is equal to summation of j equal to 1 to n on the, so one side I'm writing it like this, that this will be xk a kj xj plus summation on the other side I equal to 1 and 2 n x I a ik and xk. So now this can be written as, see, x is varying. So if you see here xi, here xi is varying from 1 to n, and here xj is varying from 1 to n. So both I and j are varying from 1 to n. So both can be clubbed into 1. So this we can write as sigma, let this be only one variable, I equal to 1 to n. And then we can write it as xi into akj plus, no sorry, xk into akj plus aik into xk, because k is not there. If this is clear, so this j, okay, pay attention, j will vary from I to n. So it will be x1 x2 till xn. Here xi will vary from 1 to n. This will be x1 x2 till xn. So both are common. I have just brought this in one part, and then remaining part I have left it as it is, xk into akj. This is as it is, and then second part, this is as it is, xik into xk, aik into xk, because k is not changing here. This is the one fixed value I'm taking. So now why I have written it like this, that I'll just change 1 to n xi, and this will give me the complete thing. Now let's, okay, do a dy by dx. So this will do a partial derivative with respect to xk. That's what we wanted to find. Then let's find the partial derivative with respect to the kth element. And sum it up across j and I and j, whichever direction. So this is your dy dxk. So you can see here also, k will factor here also, and k will come here also. Similarly, k will come here also, k will come here also. Okay, I'll revisit this now when I'll be talking. So dy by dxk, can we write it as sigma I equal to 1 to n xi. Now xk is a constant, right? With respect to k, xk is a constant. So this derivative will become 1. Not constant, sorry. This is like x only. So x, okay. So the dy by dxk with respect to xk, this will be 1, and this will be a constant, into akj plus aik into 1 right. And now I have moved this j also, I have made it as I, right? So I have clubbed this up. So there also I'll change here also, sorry. Okay, notice. So j I have removed, got rid completely, I have replaced it with I, because both are moving in the same. So both the places has ik. This is ki and this is ik. So this is equal to nothing but summation I equal to 1 to n xi. Okay. So this is xi I have written it this way. So this is xi, and this will be aki plus aik. Xi I'll write this side because for vector multiplication, because the dimension should match. Okay, so let's pull it side, this side. Dimension should match for multiplication, right? So this matrix, and this will be n cross n, this will be n cross 1. Only then this n and n should match. So I have to write it this side, this way. Be careful of the matrix notation, matrix and vectors. The dimension should match for multiplication when I'm writing it as multiplication. So the location will matter, otherwise it won't be multiplicable. And now let's come. This is aki. So I is varying from aki and aik. So what is the aki? I is varying. So here also, if you see in this a also, if there will be a21, there will be ak1, ak2, like this till akn, right? And here also there will be one a12, a1n. So there will be one a1k, a2k, like this till a2 ank, ak1, ak2, akn, a1k, a2k, so the order is reversed because it is a transpose. And do you see that I'm getting in the same format, ak1, ak2, and then a1k, a2k. So if I sum this across all the i's 1 to n, so this is just showing me one row of a, this is showing me one row of k. This is one row of a, this is one row of a transpose. Okay, where is it? This one. Now if I sum it up across all of it, then will I not get a and a transpose matrix completely? If I do it for all the n here, will I not get a and a transpose? So finally here, so for that I have to sum this x k from I to n. This is the, I have taken one unit. So now for dy Be careful, okay? Dy by d, okay, let me write it very carefully now. Dy by dx can be written as summation I equal to 1 to n dou y by dou, not I, not I, k is equal to 1 dou xk. So if I take the derivative for all xk to k from 1 to n, I'll get this. That's what I wanted. Dy by dx, what did I say? This is dy by x1, x2, xk, xk. So if I move k from 1 to n, I'll get dy by dx. This is how we have defined. That's what I'm writing. And this is what we'll get when we will do this. This will be summation k equal to 1 to n, summation I equal to 1 to n, aki plus aik into xi. So this will finally become a plus a transpose into x. So your dy by d x transpose ax by dx is equal to this. We have proved this now. This is a long, derivation, but this is what it is. This is very common and very frequently used. I wanted to prove this to show you that these can be proved from ground up. I hope this is clear. And if A is equal to A transpose, then if it is symmetric matrix, here A and A transpose may not be equal, but if A is equal to A transpose, then this will become equal to 2AX. So d by dx of x transpose AX will become this. Okay, I hope this is clear. We just took the kth entry and then we saw that it changed around both the directions, and then we just plugged in all the values. Okay, if it's not clear, just do the derivation once yourself and then you can get it right. So this is your another derivative where a function is mapping from a vector to a scalar, but that may not be always the case. So if this is clear, okay, this is enough. Now you can check all the variants of vector derivatives. Now let's take a step ahead and move to another example where the output of a vector may not be a scalar. So the function that is mapping, so there is a function fx. See, this is ax, where A is a matrix which belongs to n cross n and x belongs to n dimensions. So what will be the final dimension of this is m cross n. This is n cross 1. So what will be the dimension of this? This will be m cross 1. So can I say this function is mapping my vector of n dimensions, and the output, final output will be of m dimensions. So can I say that I am mapping a vector from n dimensions to m dimensions? This is not a scalar, and this is called vector valued function. So earlier these were called scalar valued functions because the final value that we were getting was a scalar. Here finally I am just changing the dimension of the vector. So these are called vector valued functions. Okay, so be cautious. So we are not getting a scalar, but we are getting a vector of n dimensions is transformed by a matrix to m dimensions. So input is a vector and output is a vector. So vectors dimensions are only changed, and when we take a derivative of this, so that has got a special name, and that is called what we call a Jacobian. So we get a Jacobian. So when we take the Jacobian is defined for this, okay, for such kind of, so not for a scalar context, but here here a Jacobian is defined. So Jacobian, what is a Jacobian? This is nothing but for such matrices the derivative, okay, dfx by dx is equal to, this will be equal to the dimensions of the matrix, and here we have dou f1 by dou x1, dou f2, these are partial derivative dou x2, like this till dou f1 dou xn. This is a m cross n dimension, that is same as your matrix dimension. Similarly, this will be dou f m. We'll calculate the value of the function at mth point, and we'll get dou x n, okay, because that is there, and this will be dou fm by dou x1. This will be dou f2 by dou x1, dou f2 by dou x2, and like this and like this. I hope this is clear. So this is all x1, x2 to x1. The denominators are moving from on the n dimension, and the numerators are moving in the m dimension. So here in this dimension, this is m rows, and here this is 1 to n columns. And finally, if we take a derivative Jacobian of it, this is a Jacobian is defined for such vectors, okay, and for such functions, this function, okay, and this is called a Jacobian. If you see here, this is your, what was your, sorry, what is m and n here? So this is n is your input dimension, and this m is your output dimension. That's what it is, right? Your n is your input and the function is your output. So finally, output by input dimensions, Jacobian, you will get, which will be partial derivatives with respect to this. I hope the Jacobian part is clear. Okay, so there is a note, quick note, that even we can say the Jacobian will be defined also for a scalar, because we can say that that will be m cross 1, right? So if we have f of x which maps r of n to r scalar, so what will be the Jacobian of this? So the dimensions will be output by input, sorry, r of n to r of 1. So what is the output dimension? The matrix will be of output into input dimension, that will be equal to 1 into n. Earlier when we took a gradient, what was the dimension? You see, output was a n cross 1, n cross 1. This was your gradient, just check it. So gradient is n cross 1, it is the same dimension as the vector. If the vector is Rn, then we are for a scalar this is defined. But for, if we are talking in terms of Jacobian, then this is output by input, and this is a row vector instead of a column vector. The vector of the Jacobian output is nothing but gradient transpose, or gradient is nothing but Jacobian transpose. You can write like this. So we write Jacobian for a scalar valued, so that is for a scalar valued, which is scalar valued function, that is mapping Rn to R. So this is equal to, so this will be equal to gradient transpose or a row vector. Okay, so we'll get the same thing, del f by del x1, del f by del x2, like this in a row. So your Jacobian will be like this. This is denoted by j, del f by dou xn, like this. So that's how it is defined, because of the way it is defined. So it is there, but generally for single for scalar valued function, we just talk about the gradient. Okay, and the Jacobian is defined for a vector valued function, where it is changing the vector's dimension from one dimension to another. Okay, so that's when we talk. Otherwise, we'll talk always about the first derivative. If it is a scalar valued function, we'll always talk gradient. I hope that is clear. So this is a m, and what is it? This is m by n matrix of first order derivatives, and it will give me the best linear approximation of the function at a given point. So what is the function at that point? Okay, it will give me a best linear approximation of that. That's what it does if I take the derivative of that. Okay, if this is clear, so just an extension of this is what is called Hessian for second degree. But Hessian is defined for scalar valued function only. That is defined only for scalar valued function. Okay, defined for scalar valued function. So these are just the names, you should know this. This will come again across it again and again. Scalar valued function means a function that is mapping Rn to R, and this is your the matrix of second order partial derivatives. This is your matrix of second order partial derivatives. So partial derivatives are very important. I told you it's very simple. It's just the derivative. Just take the other variables as constant and take the derivative. That's what is partial derivative. Nothing, no rocket science behind that. And what does the Hessian say? Because whenever we are talking of second derivative, it will just give me the curvature of that function at that point. Okay, it will give me the curvature. It will give me the curvature of that function. From there only we define the maximum minima, right? Which direction it is going? It is going up or down. Curvature of a function. It gives me that. If the curvature is positive, then it's upward curve. If it's positive, this implies this is a upward curve. This implies something of this sort. Upward means this will hit a point of minima, and we know that second derivative of a minima is positive, and negative means downward curve. So we have discussed this in the maxima minima, all these concepts in detail in my calculus video. I'll put the link. So negative means downward, means it is here and now it is going downwards. The curve is going downwards. That's what that Hessian means. Okay. So let's define it formally. So there is a function f which maps. This is a scalar valid function which maps a vector to a real number. Okay, to a scalar, and my x belongs to n dimension. This is my vector x. Okay, and the first derivative. Okay, what is my first derivative? The first derivative vector is a gradient, and this is generally given by del f or del xf. Okay, whatever you test. Generally, the simple form is instead of x is overhead, we write del f. Okay, and the del f also we know that is, we have seen that belongs to a n dimensional vector because it is dou f by dou x1, dou f by dou x2. Here only we have seen, right? It is transpose of this. So this is also like this coming. This is a column vector, right? Even the derivative is like that. So your gradient is also Rn. So what will be my second derivative? So second derivative will be nothing but, so now you are mapping. So now this function, this derivative function, what is it? So if I say, if you see this quickly, so just the word play, okay, just get the word play here. So your derivative, first derivative, okay, this is mapping nothing but a vector Rn to Rn, because your derivative is also Rn, the vector is also Rn. So the first derivative mapping from Rn to Rn means it is a vector valued function now. Vector valued function, because we are mapping a vector to the same dimension, but it is a vector valued. We are getting vectors output. Valued means whatever is the output of the function. Okay, whether it's a scalar or a vector. That's what it means. So this derivative is a vector valued function. So now second derivative can be said that is a Jacobian of the gradient vector. So the input to this is the gradient, and if I take a Jacobian of that, that will be my Hessian. So my Hessian is defined as that the second order, right? So it's a derivative of derivative. So Hessian, if we say, this will be my, generally it's written as del square f, and or in partial derivative dou square f by dou x transpose, that is the square x by x transpose. Generally x square is equal to x transpose x. Okay, so ulta. Okay, so whatever order you take. Okay, and this we can say this is equal to Jacobian of gradient. Because this is Rn, so this is just, so Hessian is nothing but a Jacobian of the gradient, and that is the second order derivative. And in terms of vectors, matrix, it is written like this. And let me give you an example. So how we write, h is equal to del square f, this is equal to dou by dou x transpose, and then dou by dou x of f, like this, and this is equal to nothing but all the second order partial derivatives. So this will be dou square f by dou x1 square, second order. Okay, and then this will be like this, second derivative dou square f by dou x2 square. Here it will be dou square. Okay, I'll read this. So the diagonals will be all square terms, so it will be till dou square f by, because both will be same, dou x square n, and this one will be dou square f by dou x1 dou x2, like this, till dou square f by dou x1 dou xn, dou square f by dou x2 dou x1. So just this becomes cumbersome. x1 x2 is x2 x1. Okay, and it will just continue this side. So I hope you can fill the matrix now. The numbers are matrix, dimensions are, if it is n, this will be n cross n, 1 2 like this till n, here 1 2 like this till n. This will be n cross n square matrix. Okay, and mostly in machine learning, all will, when we are dealing with covariance matrices, etc., mostly this will be a symmetric matrix. Okay, this will be mostly in, so there's a note, in ML mostly we will be dealing with symmetric matrix. So what does a symmetric matrix mean? That anything across the diagonal are same. So this value and this value will be same. This value and this value will be same. So all the diagonals across that, everything will be same. So how do we write it mathematically? So we can write that dou square f by dou xi dou xj is equal to, if it's symmetric, then that is dou square f by dou, I take it in any order, dou xj. Okay, this implies even my Hessian will be symmetric. So even my Hessian will be a symmetric matrix where H is equal to H transpose, because these entries will be same for the matrix, because the input, whatever we have taken, these matrices, the gradient will come out to be symmetric matrix. Okay, so I'll give you a small example. This is nothing but a second derivative. So for example, simply put, right, this is nothing but a second derivative. So let me give an example. For example, my same example, fx is equal to, so this is important, that the second derivative should exist at least, right? So if I have then define a scalar value, so this is should be for a scalar valued function, and the second order derivatives should exist, otherwise it won't make sense. So only then we'll take x transpose ax, only then the second, this is of square degree, x transpose x variable c, this is like kind of x square. Okay, it's similar to x square, and there's a matrix for changing the dimension. So where, and also I'm telling that A is symmetric, and my x belongs to n dimensions. So what will be my first derivative? So gradient, this is equal to your gradient. Okay, so this will be equal to dou f by dou x, and this will be equal to, we have seen this is asymmetric, so we have calculated this already. This is 2ax. Okay, because A is symmetric, but this was equal to A, this was equal to A plus A transpose into x, right? But here A is symmetric, that's why this is 2ax. So what will my second derivative? Del square f, this is your Hessian. Second derivative, nothing but second derivative. This is your Hessian, and this is the Jacobian of the gradient. So this will be nothing but del square f by del x transpose. Okay, or let me just write. So this will be, so with respect to x I have done, and now let's do it with respect to x transpose of this. That will be, so this is a gradient, first derivative I have, and the second derivative will be just the derivative of this with respect to x transpose, and this will come out to be equal to 2a only. Okay, so this is nothing but a second derivative in terms of matrix. Okay, so this is your Hessian. I hope this is clear. Second example, simple example, I'll give one more so that it becomes clear. So your example is like, for example, there is a multivariate f is equal to x square plus y square, two variables. So my gradient is del f, this is equal to across all variables dou f by dou x and dou f by dou y. Now let's do. So here if I do a partial derivative of this function with respect to x, then y will be constant. So this will become 2x. Similarly, this will be 2y, because x is there. So this will become 2x, y is constant, so this will be 0. Similarly for y, the other way around. So this is there, and then what will be my del square f? This will be equal to Jacobian of this del square f by del x square, then it should be del square f by dou x dou y, then dou square f by dou y dou x, and then there will be dou square f by dou y square. Okay, if it is symmetric, then both will be same. So let's do it. This will be equal to, so dou square f by dou x square. So now I have to differentiate this. I have one derivative already, so differentiate it once more with respect to x. This will become 2, and what will be its derivative with respect to dou x is already there, and if I differentiate it with respect to y, so 2x is a constant with respect to y, so dou f by dou x is already done. Now I have to do dou f by dou y. So this will be 0 because x is constant with respect to 0. Similarly, this 2y, so dou f by dou x is already done, that is 2y, and dou f by dou x will give me 0. This is constant, and similarly it will become 2 now. Okay, because dou f by dou x, dou f by dou y is already done, and dou f by dou x will be 0 because y is a constant with respect to 0. Similar concept. So this is your final Hessian, and this has got very beautiful properties. Okay, if the determinant of this is greater than 0, then this is these 2 points are your minima. Okay, if the determinant of this is less than 0, then that will be a maxima, and if these values are like not less than 0, if it is greater than or equal to 0, then that's a point of optima. And if it is these two are like of opposite signs and it's giving me a negative gradient, negative determinant, then that will be a saddle point. Say this is x square, this is minus y square, so this will be 2, this is minus 2, so that will be a saddle point. Okay, so that's all here. So let's come back to let's proceed to matrix derivatives now. So I hope Hessian is clear with this example. This is nothing but second derivative of a vector of a function, second derivative of function that is scalar valued, means it maps a vector to a scalar. That's where your Hessian is defined. Okay, and we saw 2 examples. Okay, so now let's move to the next topic, that is your matrix derivative. So your matrix derivatives. So now we'll take the derivative of a matrix with respect to matrix. Till now we were dealing with vectors. So all the functions are mapping a vector to a scalar, vector to a vector, like that. Mostly we are dealing with vector to a scalar. So that will be our word, and that's why you will not listen of Jacobian much. But Hessian will talk, because gradient is defined for vector to a function which maps vector to a scalar, and Hessian is also defined for vector which function which maps a vector to a scalar. So you will listen about gradients and Hessians, but Jacobians are not discussed much because in common practice you won't interact, you will not get such functions much. But it is present when you read papers, right? You will see mentions of Jacobian in that, and you should know what it is. So the terms you should be aware of. Okay, on that note, let's proceed with matrix derivative. So what is a matrix? We know. So I'm writing all these things again and again so that it becomes amply clear. So this is your simple matrix, A11, A12 till A1n. This is your AN cross n matrix. This is your AN1, A21, like this. So this is your simple matrix, we know that. And let there be a function. So again, this matrix derivatives are defined for any function that maps a matrix to a scalar value. So let's define a function that maps, okay, there's a function A that maps a matrix of dimension m into n to a scalar dimension. This maps a matrix to a scalar. So for example, what will be the kind of function that we'll see? So for example, if you have a trace of a matrix, where if it's a square matrix, then it will be the sum of all the diagonal values, determinant of the matrix, that will give me a scalar value. So we have derivatives defined for such functions. Okay, so this is a function that maps a matrix to a scalar. Okay, we'll see an example, then you will get it. Okay, so here, so we will do a derivative. So here, derivative with respect to A will be equal to nothing but dou f by dou A11, like that. with all the values, dou a12 like this till function with dou with respect to a1n, and function whatever is the function with respect to dou ann. Okay, if it is mn, then dou a mn if it is m cross n. Okay, and this will be dou f by dou a m1 like this. Okay, all the partial derivatives with respect to each term of the matrix. So just replace all these, okay, whatever is in matrix with the partial derivative of whatever function is mapped with each entry. Okay, the dimensions of both will be, oh, this is a square matrix. Okay, okay, I will make it a so because the definition is m cross n, so I'll make it m cross n only. So this is simple. I'll just change this to am1. So here you have 1 2 till m, and here you have 1 2 till n. Here also 1 2 till n, and here 1 2 till m. So that's why you have n cross n. Okay, so this is how it is defined. Just simple with respect to each term, each entry at each ij location, and that's what will give you your partial derivative. Simple. Let's understand this with an example. For example, there is a function f of a that is equal to here trace of the matrix. So we know trace of the matrix is what? It is defined for square matrices, and plus it is the sum of diagonal elements. Like this. So if your A is equal to square matrix a11, a12, a1n, ann is n cross n, this is an1 like this, so this is a22 like this. So your f of a is equal to trace of a is equal to a11 plus a22 plus a33 plus so on till ann, all the diagonal entries. This is how we have defined. So now this matrix of m cross n, n cross n square matrix has been converted to a scalar because these are all scalar values, and I'm just summing them up, so final value will be scalar. So this is a function which is mapping a matrix to a scalar. Okay, the function definition holds. So now we have to calculate the derivative. Dou f by dou a is equal to what? So simple, we know that this is equal to, I'll just copy this. So we need to calculate this. This is there, and here I'll make it as n1, and this is nn, and this is your n cross n matrix. Okay, here also this is n. Okay, square matrix, all these terms are here. This is your dou f by dou a22 like this. So diagonal entries are there. So the trace contains sum of all the diagonal elements. Okay, so this is there. So now if this is the function. Okay, just look at this carefully. This is the function, and I have to take derivative of each point. Now let's go one by one. So if I take the derivative of this function at this point, dou f by dou a11. Okay, so it will be my let's do only one, and then you will understand. Dou f by dou a11 of dou by dou a11 of a11 plus a22 plus so on till ann. So now tell me anything apart from a11 first term, others are 0. They are constant for a11, right? They are not changing, so this is the only thing. So with respect to a11 this will be 1, and for the others it will be 0, right? For all it will be. So similarly, which all terms? I'll get a 1 here, I'll get a 1 here, I'll get a 1 here, and all other terms will become 0 0 0. This will all be 0. So here all the diagonal elements will be 1, and other terms will be 0 because they don't figure in this equation at all, because matrix is defined only for diagonal elements. So wherever I is equal to j, I'll have 1, and if I is not equal to j, I'll get 0. What kind of matrix that is? Where I equal to j means that all the diagonals are 1 and rest all the elements are 0. So this is nothing but your identity matrix. Okay, So your dou f by dou a1, this is equal to 1. So this implies your dou by dou a of a trace of a matrix is equal to identity matrix I, where this is equal to 1 for if I is equal to j and 0 if I not equal to j. Okay, I hope this is clear. So this is your partial derivative of a matrix. Okay, so this is what I have. So let's do a quick revision. So what all things we discussed here, important things. So we are discussing matrix calculus. So first thing we start with vector derivative. So a vector is defined as x1 to xn. This is an n dimension. Okay, this is an n dimension vector Rn, and any function. So what is the vector derivative defined for? The definition is any function which maps a vector to a scalar. Okay, so this is a scalar valued function. For that a derivative, vector derivative is defined, and that is called the gradient of the vector, and that is your dou f by dou x1, dou f by dou x2 till dou f by dou xn, and that is also a n dimensional vector. Okay, that also exists in n dimensional space. So this is your first thing, and then we saw proof for A transpose x, because that will be a scalar, and then x transpose ax. This was a big derivation. I hope just go and follow it again. If you didn't follow this time, do it yourself. Okay, we did this cumbersome, and then we found that this is equal to a plus a transpose x, and if a is symmetric, then a will be equal to a transpose, and that will be equal to 2ax. Very common, you will see it all the places. Then next is, we saw that there can be a function, like if you multiply a vector with a matrix, then it will not be a scalar but a vector. So if there's a function which maps a vector of n dimensions to a vector of another m dimensions, then they are called vector valued functions. And if we take a gradient of that, so there is a special function derivative for that. There's a special function name for that gradient, that is called Jacobian, and the matrix is called Jacobian matrix. So this is called a Jacobian matrix. So this is having all the gradients. So this is only for vector valued, where a m dimension vector is mapped to a n dimension vector. So we have all dou f1 by dou x1, dou f2 by dou x2 till dou fm by dou xn. So this is just Jacobian. So important point is that it is defined only for vector valued function, not for scalar valued. And if we say that if n is equal to 1, so this will become a scalar valued, right? So the Jacobian will give me the gradient transpose, because it is giving me a row vector's output. This is spreading it out. So the output of a Jacobian is a row vector, which is a transpose of the gradient vector, which gives me a column vector. Okay, this will give me a R of 1 cross n, and the gradient is only Rn, n cross 1. Okay, that's fine. So we saw that. Then we saw Hessian. Hessian is nothing but second order derivative, and this is defined for a scalar function value which maps a function of n dimensions to a scalar. And we saw that it is nothing but all the second order derivatives of a vector. So we took all those second order derivatives, and if it is symmetric, then even the Hessian is symmetric. If the this gradient, the Jacobian is symmetric, sorry, the gradient is symmetric, then even the Hessian is symmetric. Most of the ML are ML Hessians are symmetric. Then we saw an example of x transpose ax, where a is symmetric, and then we calculated this. And then we saw one more example, and then we saw this, and then we saw matrix derivatives, where similar to a vector which was defined for a function which maps a n dimensional vector to a scalar, matrix derivatives are defined for a function that maps a m cross n dimensional matrix to a real valued scalar. Okay, to a scalar. And that is this. We saw that this is all the it is with respect to all the values of the matrix. We take that partial derivative at each entry point. So it is same at all the entities. They are just, we take the partial derivatives, and that is what the final matrix that we get. That is nothing but your partial derivative with respect to the matrix itself, and that's what is called matrix derivative. See, the derivative is not with respect to x, but the matrix itself. That's the difference. And then we saw an example of trace of the matrix, which is the function which maps the the matrix m cross n matrix to a scalar, because it is sum of all the diagonal values. And we saw the derivative, that derivative of a trace is nothing but an identity matrix where all the diagonal values are 1 and rest everything will become 0. Okay, I hope this is clear. Okay, that's all for matrix derivative. Thanks for watching this video. Have a good day and bye for now.